All right, so here is our very first day of notes, Unit 1. As you can see from the title, this is all the building blocks. So this unit, it kind of sets our foundation, mostly for vocabulary purposes and all that kind of stuff. I know I harped on the very first day of class about like showing your work. Today's notes don't really warrant showing work because it's mostly a vocabulary lesson. So just kind of keep that in mind. So first of all, we're going to start off with this guy. His name is Euclid, and you're talking around 300 BC. No one's quite sure when he was born, but he's considered the father of geometry because he's kind of the one that started writing stuff down, which was a challenge for him because he had to start writing definitions for mathematics, specifically geometry, and that had never been done before. So he was imagine trying to write definitions of very technical words when nobody had a foundation for any of these words yet. And so he came up with the 3 undefined terms of geometry, and you need to know them. And they are point, line, and plane. And we're going to talk through those at length here in just a few minutes. But they were called undefined terms, not that they can't be defined, but they were like the 3 building blocks of all geometry definitions. So if you know what a point, a line, and a plane are, then you can basically build definitions to infinity, right, for all other things that are geometry based. So he called them the 3 undefined terms, point, line, and plane. And so we're just going to talk about those. So a point, first off, is a location in space. It doesn't have any dimensions, so no length, width, height, any of that good stuff. And when we draw a point, though, we have to represent it with a dot or a vertex. So on paper, right, it would either look like an actual dot, and it is always named with a capital letter, right? So if I put like an A next to that dot, right, we would refer to that as point A. Right. Please note that it doesn't always have to be a dot, right? When we start getting into shapes, right, like triangles, let me draw a nicer triangle there. When we get into triangles, right, you of course know that the sides of a triangle, they meet at a common point called the vertex. And so those would then have labels. You're not going to see like big bold points at the tip like that, but just knowing that that vertex does represent a point, and those would also be labeled with capital letters. Okay. All right, a line is if you were to take infinite points, right, and put them all together, right? So a continuous arrangement of infinitely many points. It does have one dimension, obviously, because it has infinite length, okay? In order to name a line, which you'll be doing a lot of, right, you can use any 2 points on the line to name it, right? It doesn't matter how many points. So if I were to draw a line, which of course it must have arrows on the ends if it's a line to represent that it goes on in opposite infinite directions, then we're going to name it using any 2 points that lie on it. Now, there are obviously infinite points, right? I could keep that make up this line, right? And so we can't obviously label all of them. So even if you have 3 labels on there, like let's say you have points A, B, and C that are specifically shown to you on this line, when we name it, we'll just pick any 2 points, right? So line AB, and then we use the symbol for line, which of course is just a short little line written directly above the AB, right? Or you could use BC, right? Or you could name it AC, right? It doesn't matter as long as you just pick any 2 points. You would not write line ABC, right? We do not name lines with 3 letters, even though there's 3 letters on it, right? We only pick 2 of them. And the order does not matter, right? If I said line BA, right, I'll write that down here. Order does not matter. Right, so if I said line BA or line CB, we would all go and be looking at the exact same line, okay? There's one other way we can name lines, and that is with a lowercase letter. It kind of usually looks like a little script or cursive letter almost, if it's near one of the arrows. So the first way, I'm gonna kind of put sorry about that, is with 2 points. And the second way is to just physically write the word line and then use the lowercase letter that's written by one of the arrows. If you don't see a lowercase letter next to one of the arrows, then you'll use the first method, right? But either one of those is appropriate to describe a line. All right, in geometry, there are postulates and theorems, and our good friend Euclid up here, right, he is the one that wrote all of the first postulates and theorems to get the ball rolling for geometry. Okay, so we're going to talk about the very first postulate, and that is a statement that is assumed to be true without any proof. Right, that's what a postulate is. Right? It's a statement that we have to assume is true without proof. And it's not that, it's basically because it's so simple that you can't prove it, right? It's such a simple concept. You just have to trust that it's true. Okay? Now, a theorem is the opposite, right? A theorem is a true statement, but it's true because it can be proven. Right? In science, you would call them theories, right? Like the theory of relativity or the theory of gravity, that kind of stuff. But in math, we typically call them theorems, right? But these are things that can actually be proven. Okay? So now that we know the difference between a postulate and a theorem, we're going to go look at Euclid's first postulate, which again, remember, is kind of like a common sense statement that we just know is true because common sense tells us so. And it's through any 2 points, there is exactly one line. Right? And this is true and I didn't say this earlier, the class that you take in high school is called Euclidean geometry, named after Euclid. There are other types of geometry. So these theorems and postulates that we're learning are only true for the geometry of this class, right? If you take a higher level geometry like in college, well then these rules all change. So through any 2 points, there's exactly one line, right? And that should make sense, right? If I have 2 points in space, just floating around, I will always be able to draw only one unique line, right? Lines cannot be curved in Euclidean geometry, right? So there's only one unique line that can pass through them, right? And we can't really prove that, right? It's just common sense. All right, his first theorem was that if 2 lines intersect, then they intersect in exactly 1 point, right? And that actually can be proven. It's not a very fun proof to write, but it is clear, obviously, that if you have 2 intersecting lines, because lines have to be straight, going in infinitely opposite directions, well, then they can only intersect at exactly 1 point. Okay? And again, that can be proven, so we call that a theorem. All right, next up, our next major definition here is collinear points. Now, obviously, the prefix co, right, means to share or together, belonging with one another, right? Like a co-worker, right, is someone you work with. You share your workspace, that kind of thing. So collinear is exactly what it sounds like, right? You're sharing points on the same line, okay? So if you look at this little diagram here, we've got 4 different points labeled here. So we're just going to do some yes, no's, right? So the first question, are A and B collinear? Well, do they share the same line? Yeah. So we're going to say yes. Sorry, I'm a total perfectionist and everything's straight. All right. Are C and D collinear? Yes. Now, I do agree that this is not like, it's not a full line, but it doesn't have to be a line, right? It can be a part of a line, right? So we know that we can see that there is a line that they share. If we wanted to extend it infinitely, we could, so that's not a big deal. All right, are B and D collinear? Now, this one is tricky at first for a lot of people. Most people say no, but the answer is yes, right? Now, I know that there's not an actual line drawn, but collinear means that they can share the same line. And as Euclid stated up here in his first postulate, through any points, there is always one unique line. The line does not have to be drawn, okay? So any 2 points in space, according to that first postulate, any 2 points are collinear. If the line isn't drawn, that does not matter, okay? And that is my little deep thoughts bubble over here that I'm going to write any 2 points are collinear. Okay, and I'll even go so far, I'm going to write the line does not have to be drawn. There we go. Okay, so that is a definite yes. And then our last question, are B, C, and D collinear? Well, here's B, C, and D. Can I get a straight line through all 3 points? No. All right, so that is a no. Now, can 3 points be collinear? Absolutely, right? We even drew that up here, right, in this example, right? In this picture, A, B, and C are collinear because they share the same line, okay? So 3 points can be collinear, it's just in this picture they are not, okay? So just remember, any 2 points are collinear, right? So if any time you're asked about 2 points, the answer is yes. Yes, 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 always a yes. But as soon as you add a third or a fourth point or whatever, the answer is like, I better go look at the picture just to make sure. Okay, and then of course right here, this is telling us that points that do not lie on the same line are non-collinear points. Okay, so that's stemming from here. We would call those non-collinear because they do not share the same line. All right, so that's kind of everything based on lines and points. Those were our first 2 undefined terms. And then our third and final undefined term is a plane. Okay, so a plane is a 2-dimensional surface, right? It's basically you're putting a lot of lines together, all side by side by side. It extends infinitely in all directions. Now, it's easy to draw a line that looks like it goes on forever because we can put arrows on the end, but as soon as you want to draw a flat surface, that's pretty difficult to draw. So typically in this class, we'll use a parallelogram, all right, this guy right here, or you can just draw a plain rectangle, and that will just represent our flat surface. We can't really sit here and draw arrows, you know, all over the sides to tell our reader that it goes on forever and ever and ever. We just make that assumption, okay? A plane is named using any 3 non-collinear points. And I'm going to highlight that because that is super important, right? They have to be non-collinear points because if I just pick 3 points and they all lie on the same line, and I want to name a plane with those 3 points, there's actually infinite points, right? I could slice through here. My picture's not going to be really great here, but I could slice through this plane with another plane going through those exact same 3 points. So when I name something, it has to be perfectly unique to that something. So if I want to name a plane, I can only pick points that lie in that plane and no other plane in the universe, right? So they have to be non-collinear points. So just kind of scatter those around. I'm going to label this X, Y, Z. They can be any letters you want. And then we would just simply write, if we were describing it on a piece of paper, we would write plane X, Y, Z. Okay. Again, the order doesn't matter. I'll write that over here. Order does not matter. Right, I can say ZYX, YZX, YXZ. It doesn't matter. As long as the points are non-collinear, you're good. All right, and just like lines where we also had that second option, here's option number 1. Option number 2 is sometimes with planes, you might, instead of having to deal with all the points and stuff that are all around the place, you might actually have a capital letter, and it will also look kind of cursive or script looking, in one of the upper hand corners. So let's say if I have like a fancy looking capital D in the corner, then I can also just call this plain D. Now you have to be careful because, that's a weird looking D, let me fix that. I don't know if that's any better. Because it's a capital letter, you have to make sure you distinguish between that's not a point and that it's actually naming the plane as plane D. If it was a point, it would actually have a dot next to it like we talked about earlier, right? So that's how I know that that's in the corner naming the whole plane, okay? And if you couldn't guess it, points that lie in the same plane, they're called coplanar, right? Just like collinear, sharing the same line, coplanar, sharing the same plane, okay? All right, and wouldn't you know it, we're back to Euclid. He made more postulates based on planes. All right, so he says through any three non-collinear points, there is exactly one plane. Okay, and that's exactly what we just talked about, right? If 3 points are non-collinear, there's only one way to slice through 3 non-collinear points in space, right? So that produces a unique plane. And the third postulate, I guess, that we've talked about, if 2 points lie in a plane, then the line containing them also lies in that plane. All right, so that's kind of wordy, but what that's saying essentially, we can just draw a quick illustration of that. There's my plane being represented by a parallelogram. If you have 2 points that lie in the plane, then the line and all of his infinite points that pass through those 2 points, he also lies in the plane. So if you see a picture like this, we are assuming that that line and all the infinite points that exist in that line also exist in that plane. Okay. And then our final postulate, I believe, is if 2 planes intersect, then their intersection is always a line, right? And you can kind of see in this picture, right? Remember, the planes go, I know they look like rectangles and parallelograms, but they actually go on forever and ever and ever. Notice it looks like almost like a 3-dimensional plus sign, right? You've got this like plus sign happening, but it's got depth to it. So we have these 2 planes intersecting, and if 2 planes intersect, they will always intersect at a line. Okay, they have all those infinite points in common that lie along that linear intersection. All right, really quick, we're going to practice sketching some stuff. You are going to be asked to sketch some pictures on a quiz or a test in the future. So we're just going to kind of practice that really quick. So sketching planes that do not intersect. Okay, well, things that don't intersect would be parallel. So in essence, we're drawing parallel planes. Right? Now your sketches don't have to be awesome, right? You've got kind of 2 choices. I'm going to draw a, oh, that's weird, sorry. I'm going to draw a parallelogram. There we go. And then you have 2 choices. Copy. I'm going to just draw one directly beneath it, like this, right? Or if you want, you can draw another plane and you can overlap, right, like this if you want to. Again, these are optional. And then what I would want to do if I overlap them is I would want to kind of dash what would actually not be seen because it's hovering underneath that top plane. Right, so those are kind of your 2 options. If you see 2 pictures that look like this, one or the other, then you can assume that they are parallel planes. So one is hovering above the other and they will never intersect. Therefore, they have absolutely no points in common. Okay. The next one tends to be the hardest for people, sketching lines that intersect, which is this picture right here. So if you want to just copy that, you totally can. The way that I like to do it is I just like to draw a rectangle. Sorry, my pen keeps skipping on the screen. So I like to start with a rectangle, and then I like to, before I draw the second plane, I like to draw the line where the 2 planes are going to intersect. Because actually the most important part are these 2 points right here on the sides. Because if my rectangle contains those 2 points, then my second plane that I'm about to draw also needs to contain those 2 points. So then what I'm going to do is I'm going to draw a parallelogram kind of just over the top of that rectangle and make sure that he also contains those same exact points. Okay, so now it kind of looks like a 3-dimensional X, right? And you can clearly see that line where they are intersecting. If you want to dash what's behind that you can't actually see, then you can. When my eyes kind of cross when I keep looking at this, so I'm not going to do that. It's not a requirement. All right, the last 2 really quick, to sketch a line that intersects a plane at 1 point. Okay, well the first thing I'm going to do is I'm going to draw the plane. So just some parallelogram or rectangle is fine. And if the line intersects at only 1 point, well then that means that the line has to be piercing through it. right? And so some people always do this because they put it like at the corner. But remember, you don't have to pick a corner because planes technically go on forever and ever and ever, right? So there's really no quote unquote corners. So I'm just going to draw a line that looks like this, right? So it actually kind of looks like it's piercing through the plane, right? Because I'm like stabbing the plane vertically with a line. Okay, and so that's kind of the picture. Now, here's what something I tell everybody really on the first day is to be really careful with your three-dimensional pictures that you're looking at because it's sometimes hard to distinguish what points are where when it's a three-dimensional drawing on a two-dimensional piece of paper. So, for example, if I put point A here on the line and I asked you, is that point in the plane? The answer is no, right? Because imagine like if you kind of pierced your hand with a pencil, right? That point A is on the pencil, right? It's not in the plane anymore, right? So I'm just going to write down here as a little reminder, point A is not in, let me give it a label. I'm going to call it Q. Put a little capital letter in the corner there. So point A is not in plane Q. All right, because it's hovering above it. So just be really careful. It looks like it's in plane Q because it's on a flat two-dimensional, screen, but it's technically not three-dimensionally. Okay, so just be careful. And our last one, sketch a line that lies in a plane. Well, we've already done this in one of our little postulates. So I'm going to draw my plane. And if a line lies in it, then I would just simply draw the line in the plane. And I would assume, unlike the previous picture, right, this one is actually in the plane, right? They're sharing the exact same flat surface, okay? So in this one, if I labeled this point A, right, this one is in the plane, right? Hopefully you can see the distinction between those two pictures, okay? All right, this is just a three-dimensional drawing. Obviously you can see it's two planes intersecting and then we're asking a whole bunch of questions. So I'm just gonna fly through this. If you need to pause it, you can. So are A, B, and C collinear? Yes, that is true. They're definitely sharing the same line right there. Line EF, which is right here, intersects line AC, which is right here, at point B. Yes, that looks to be completely true. Points B, C, and X are collinear. B, C, and X. They all clearly lie in that same horizontal plane, but that would be false, right? There's absolutely no way I can draw a straight line through all of those points at the same time. All right, A and X are collinear. Here's A and here's X. Is that true or false? That is true. Right, remember, the line does not have to be drawn, okay? So any 2 points are collinear. We wrote that in our little deep thoughts bubble earlier. All right, plane S and plane R, you can see that they're naming the planes with the capital letters in the corner instead of using all the points. They intersect at line M. Oh, that is correct, right? Here's that M right there, labeling that line for us, so that is true. The next one, points A, C, E, and X are coplanar. Right? Do all those lie in the same plane, or could they lie in the same plane? No. Right? Those are 4 points that there's no way. Imagine like a giant butcher knife, right? If I was trying to slice through a cake or something, if I was trying to slice through all 4 of those points at the same time, I can't do that. Right? I've got 3 random points in a horizontal plane, and then I have 1 in the vertical plane, right? And there's no way I can get through all 3 of those, or I'm sorry, all 4 of those at once. All right, next one, B, C, and E. B, C, and E, are they coplanar? Right, and that is true. Right, now, are they all lying in plane R or plane S together? No, right? But remember, coplanar, just like collinear, the plane doesn't have to be drawn. Right? It's could I slice through all 3 of these points with a plane. And yes, because 2 of them are collinear, the third point is just acting as the direction of the plane, right? So if I were to draw a plane, I know it's a horrible drawing, right? But I could totally slice through all 3 of those points at the same time, okay? So just like any 2 points are collinear, I'm going to write my deep thoughts over here, any 3 points are coplanar, because 2 of them represent the line, and then the third one gives you the direction of the plane. So any 3 points in space are always collinear. The answer is always yes, 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 yes. If it's 3 points, yes. You don't have to have the plane drawn in the figure for you, okay? And if you want to write, the plane does not have to be drawn, very similar to what we did in the last one. The plane does not have to be drawn. Okay. So if 3 points are always coplanar, right, whenever you have 4 points, you really have to analyze the picture, because it could be false, like right here on the letter F, that was false, right? Or it could be true. You have to analyze the picture. So on H, it says A, B, C, and E. So A, B, C, and E. Now this one's different from that F question because in this case, you have all 3 out of the 4 points that are collinear. So technically, I didn't really need to list all 3 because they all share the same line anyway. So of course, these are collinear, and this point E up here is my 4th point that's going to catch the direction of the plane. So this one, even though it's 4 points, would be a yes, because 3 out of the 4 are collinear, right? So that would be true. And I'm even going to put a note here, right? These are all collinear, which means I didn't need all 3 points to be listed, right? I could have just said AC or BC, right? Because they share the same line anyway. Okay. All right, so we often, on our quizzes and tests, we use rectangular prisms to represent a bunch of points, lines, and planes. So because it is a rectangular prism, we assume that these are all right angles. We assume that these opposite sides are parallel. All that good stuff is happening, okay? All right, here we go. Name the intersection of plane FGD. Okay, I'm gonna go find that really quick. So FGD. So I want the plane, so the side of the box that contains those 3 letters. So FGD would be the top of the box, right? Because it's FGD. I also got that point E there, but remember, we only use 3 non-collinear points to name a plane. All right, and the other plane is EBC. Okay, so here's E, B, and C. So that would be representing the right-hand side of the box. So those are the 2 planes they want us to look at, and they want us to name the intersection of the planes. Well, we know that planes intersect at lines, right? And so the edge of the box that they have in common would be ED. So I'm going to write ED. I am going to write the line, though, because we are talking about intersecting planes. So we are assuming that this rectangular prism kind of goes on forever and ever and ever. So we want to make sure we write that intersection as a line. All right, let me erase all this. There we go. Name the plane that intersect, or planes, sorry, that intersect at AB. Okay, so AB is here. So we need the 2 sides of the box that contain side AB. Well, clearly the bottom of the box uses AB. So we're going to name that plane. And you've got 4 letters to choose from, A, B, C, and H. Right, so you can pick any of those 4, pick any 3 out of the 4, and you can put them in whatever order you want. So I'm just gonna be like C, A, H, or you can write A, B, C. It doesn't matter. You just need to pick 3 of the 4 letters and put them in any order you want. Okay, so that would be the bottom of the box. And the only other face of the box that uses AB would be the front of the box. Right, and the front of the box contains letters F, A, B, E, so we can use any 3 of those 4, right? So I'm just going to say E, B, A. They don't have to be alphabetical, any order. You can throw the F in there if you want instead of the E or whatnot, right? But make sure you're only picking 3 letters and do not name all 4, right? Do not say plain F, E, B, A. right? We only pick 3, okay? All right, moving right along. Name the intersection of line CH, okay, that's this line here, CH, and AH. Well, we're talking about intersecting lines, and we know lines intersect at points, right? So clearly this would be H. You can write point H if you want to, but if you just see a capital letter hanging out by itself, it's automatically known to be naming a point. So whether you write H or point H, I'm good either way. All right, are A, B, and C collinear? A, B, C. Can we draw a straight line between all 3 of those points? No, right? Collinear, right? They are definitely not in a straight line. All right. Our next one, are points A, B, and C coplanar? Yes, right? They share the bottom of the box, right? So yes. Okay, sorry, cleaning up my picture. Are points F, G, and C coplanar? F, G, and C. Now again, this is one of those tricky ones. The answer is yes, because remember what we just wrote down earlier. Ta-da! Any 3 points in space are coplanar. Any 3, right? So it doesn't matter that they don't share a side of the box, because if I wanted to, I don't just have to pick the top, the bottom, the sides, or the front and the back. I can slice through this box diagonally and create a whole nother plane that wasn't originally there. Right, and so yes, they are coplanar because I can draw a plane between those 3 points. I can always draw a plane between any 3 non-collinear points. All right, and then the last question, are points F, E, D, and C, are they coplanar? So I've got these 3 are coplanar, and these 3 are coplanar, but together, can I possibly, again, think of like a giant butcher knife or something, can I slice through all of these 3-dimensional points at the same time with a flat plane? And the answer to that is no, I cannot. Okay. All right, so we've covered everything we need to know about the undefined terms, right? Remember, point, line, and plane. So now really quickly, we're almost done. We're just gonna start into the defined terms, right? Now that we know what points, lines, and planes are, now we can start writing actual formal definitions for people to understand geometry, okay? And you've heard these words before. These are not new to you. So the first one is a line segment, okay? A line segment is part of a line, but it has endpoints, right? It contains all the points in between. Now, line segments are different than lines in that, well, first of all, they're finite, right? So they have endpoints. But how we write them or notate them, for lines, you can pick any 2 points anywhere on the line to name a line, right? But for segments, that's not true, right? Because obviously there are infinite points all along the line segment. But when I name the line segment, we have to only use the 2 endpoints, right? Because we have to know where we're starting and stopping the line segment that we want to look at. And then of course, we're not going to put a line over the top, we're going to put a segment bar, okay? All right, and just like lines though, the order doesn't matter, right? So if you want to say BA instead of AB, then that would be perfectly appropriate too, right? Order does not matter with line segments as long as you're naming it using the endpoints, okay? And then we have rays, right? I'm sure you've heard this word before, right? A ray is part of a line, just like a segment, except it has one endpoint and then it extends infinitely in one direction, right? So unlike a line that goes infinitely in both directions, right? A ray only goes infinitely in one direction. Now, order is extremely important when naming a ray, right? We haven't cared about the order of the letters up until now because when we name a ray, the notation for it is a ray, a little tiny ray it's always a right arrow, always. And your first letter has to be the end point and the second letter is just some point in the direction you're going. Okay, so here, let me write that. So the first letter, when you're naming a ray, is always the end point. Now, most people call it the end point. But you could also refer to it as the starting point, right? Because that's technically where it starts, and then it goes infinitely in a direction. So whether you call it the end point or the start point, that's totally up to you, right? And then the second letter, sorry, my pencil's being glitchy, right? The second letter is a point in the infinite direction. It doesn't matter what point you pick. Right? It just has to be that I'm starting at R and I'm going towards Y forever and ever and ever. Okay? Now what you cannot do, and I'm gonna put like a big no, you know, one of these guys. Do not write YR. Right? Right, that would be starting at Y and going infinitely in the R direction. That is a totally different ray than the one that we are looking at. Also, do not, if your ray is facing left, don't make it a left-facing arrow. Right, the symbol for ray is always a right-facing arrow, always. Okay. All right, and then our last term for the day is opposite rays. Right, which is exactly what it sounds like, right? It's two rays that face completely opposite directions, right? And so if I have rays that are going opposite directions, well, then they, of course, are going to form a line, right? Because I have one ray going this way from an endpoint, and then I have another ray shooting the exact opposite directions, right? So if two opposite rays are sharing a common endpoint, then they will form a line. So if we want to name the opposite rays in this diagram, right, there's only two of them, right? It has to be the ones that are making this line right here. So both of them are sharing endpoint C. So we would say CG, again, with the right-facing arrow. And then the other one would be CD, again, with the symbol of the right-facing arrow. And that is the only possible way we could write those, right? They're both starting at endpoint C. One is traveling infinitely in the G direction. The other is traveling infinitely in the D direction, right? And it does appear as if they are going opposite directions, right? You are allowed to assume that if it does appear that they're going opposite directions and forming a line. Okay, we'll talk a lot more about that tomorrow, actually. All right. So a lot of vocabulary today, a lot of proper notation, making sure we can analyze pictures correctly, right? So just make sure that you feel pretty comfortable with all that.